Welcome to The Explainer. So, today we're tackling something absolutely fascinating. We are bridging the massive gap between advanced AI and our messy, noisy physical reality. We're going to unpack the FGSGR framework, and specifically, we're zooming in on its inverted 3D router. This thing is a real game changer because it solves a huge computational bottleneck that's honestly been holding back neuromorphic control systems for a while now. If you've been wondering how next-gen cybernetics and aerospace systems are actually going to process the world around them in real time, well, you're in exactly the right place. Let's get into it. Here's the roadmap for today. We'll start with the boundary layer bottleneck, then look at how the inverted 3D router flips the script. After that, we'll talk about hardening the architecture, dig into the residual error floor, and wrap up with some seriously cool applications in advanced systems. All right, part one. The boundary layer bottleneck, or basically how we bridge these two entirely different worlds. So, here's the fundamental question we have to grapple with. How do AI models actually process dense physical reality? Think about it. When you have this massive array of physical sensors, maybe on a robotic limb or a drone swarm, standard bottom-up processing forces the system to classify all these incredibly complex spatial geometries before it can even form a basic thought. It's literally like trying to drink from a fire hose while solving a crossword puzzle. That sheer computational load creates a massive bottleneck, and honestly, it just completely kills real-time responsiveness. And you can see the friction between these two worlds perfectly right here. On one side, physical reality is just this continuous, incredibly noisy flood of sensor vectors. But on the other side, cognitive architectures, like our frequency-governed self-graph reasoning framework, or FGSGR, they prefer to reason in discrete, squeaky clean concepts. They use typed, frequency band-tagged variables, things like observation or hypothesis. The problem is, translating that dense, chaotic physical noise into clean cognitive nodes, well, that's exactly where traditional systems completely choke. Moving on to Section 2, the inverted 3D router, and this concept of analysis by synthesis. Now, this right here is a massive paradigm shift. Instead of trying to read reality strictly from the bottom up, the 3D router uses what's called generative spatial projection. Basically, the internal cognitive system maintains a hypothesis of what it expects the environment to look like, and then it projects that expectation downward. You can kind of think of it as functioning exactly like active noise cancellation, but instead of just audio, it's for physical reality itself. Okay, so let's break down how this loop actually works in practice. First, the system generates a 3D Fourier prior. That's its mathematical belief about the world. Then, using an inverse fast Fourier transform, it projects that spatial expectation directly against the incoming sensors. It literally just subtracts its expected math from the raw observation. And here is the absolute magic of the 3D router. It only routes the unpredicted residual error upward. By only processing the surprises, the 3D router slashes the required bandwidth absolutely drastically. But hey, we all know mathematical theory on paper is one thing, right? Actually deploying it is a whole different beast. As we can see in the reporting on inverted 3D FFT routing, this brilliant generative boundary had to actually survive collision with reality. Which brings us to Section 3, hardening the architecture and moving from theory into brutal reality. You see, the original specifications for the 3D router actually failed under stress. They didn't hold up. So the researchers had to hit it with a brutal gauntlet of tests. They pushed it with the T5 boiling frog test, which, aside from being bad news for the frog, is basically a slow, sub-noise ramp specifically designed to evade detection. They also slammed it with the T6 mid-jam anomaly, where they tried to mask a real signal inside massive, chaotic sensor jamming. And checking out the results, the engineers discovered a massive, glaring problem. The original mechanism silently absorbed the exact anomalies it was supposed to be detecting. If the noise ramped up slowly enough, the system just kind of went, oh, okay, this is normal now, and updated its beliefs. It completely missed the threat. Fixing this was not easy. It required some really intense trial and error. In version 3 of the architecture, they tried to solve the problem by clipping suspect voxels based on a noise scale. But estimating that noise from the remaining clean voxels accidentally created this runaway feedback loop. The noise scale kept shrinking, which made more and more voxels look deviant until a third of a totally quiet field was flagged as an anomaly. It just completely froze the system's beliefs. So to fix this deadly loop, they literally just threw out the complex coupled estimators. Sometimes simpler is better, right? The hardened V6 architecture relies on a single robust scale, an exponential moving average of the median absolute deviation, or MAD. Because it's a median, it's totally blind to sparse outliers. You couple that with robust masked updates, and boom, you get a bulletproof 3D router that can latch onto an anomaly literally right in the middle of a massive sensor jam. All right, moving into section 4, the residual error floor, represented as rho times p. This brings us to a fundamental, absolute information theoretic boundary in the math, rho times p. This formula dictates that error reduction is strictly bounded by the common mode correlation, or the shared blind spots of your verifiers. You just can't slap infinite redundant checks onto a system and expect to get exactly 0 errors. This concept is actually known as the redundant verifier law. Basically, no matter how much redundancy you build into the system, it remains fundamentally honest about its limits. The internal architecture can flawlessly check its own math and its own inference integrity, sure, but it cannot internally prove the absolute truth of an outside premise. If a perfectly coherent lie is fed into the system and all the internal verifiers share the exact same blind spot, the system is going to accept it. Crucially, this persistent error floor, it isn't a bug in the code. It is just a feature of reality. And what's wild is that it was measured consistently across every single layer of the FGSGR project, from the spatial boundary layer to the verifier ensembles, all the way to the LLM trace bridge. It's just an architectural constant you can't escape. I love this quote because it perfectly summarizes the framework's objective neutrality. Every honest safety or inference layer merely relocates a residual it cannot remove. An honest architecture bounds and prices its residual error rather than just pretending it doesn't exist. It gives you a system that is dead on exact where it counts while being totally transparent about its mathematical limits. And finally, let's wrap up with section 5, applications in advanced systems. Because the complex math for this generative projection was optimized to run super smoothly on standard GPU hardware like the Jetson Orin, where it scales perfectly without bottlenecks, it is totally deploy-ready for real-time edge devices right now. It's no longer just a simulation running on a supercomputer. The 3D router is ready for the field. These benchmark specs actually prove what makes the following sci-fi level technologies computationally possible. By offloading the batched fast Fourier transforms directly to GPU hardware, the latency drops to the point where real-time physical control becomes a legitimate reality. And man, these benchmarks unlock some absolutely incredible physical applications. With the 3D router, we can build neural motor prosthetics that project intended limb states directly onto a motor cortex, only processing the residual neural misfires for zero latency control. We can manage massive swarm robotics by projecting a 3D harmonic wave of the swarm's intended geometry, keeping cohesion without needing to track every single drone's individual vector. We can even achieve active acoustic camouflage for stealth submersibles, or govern the incredibly turbulent plasma dynamics of atmospheric reentry shielding using active inference. The inverted 3D router makes all of this possible, simply because it only calculates the errors. So I want to leave you with this. How will shifting from bottom-up processing to predictive active inference completely redefine our interaction with the physical world? It's a massive shift in how machines understand reality. By moving from bottom-up data polling to top-down generative projection, where hardware simply cancels out what it expects and only processes the surprises, we are looking at a total redefinition of aerospace and cybernetics. Think about it. How much faster and smarter could our hardware be when it stops trying to read the whole world and starts only paying attention to what it didn't predict? Thank you for joining me on this explainer, and I really hope this leaves you wanting to dive deeper.